Yeah.
So when I submit it, you comment on my file, it's kind of rough. Yes, I fix it. Can you go check this?
Let me get this work. I'll come around later in class and check.
Yeah. Thank you.
All right, it's 4 o'clock. Let's go ahead and get started. All right, good afternoon, everyone. How's everyone doing today? Good. Sorry, I had a few technical issues in the class, but so just getting ready for today. Okay, so the plan for today is mostly to have some open office hours for you guys to kind of ask your questions in terms of getting help on the project. But I did want to go over a few things together with you guys just because I was people were asking me questions over the weekend, and I've been testing things over the last couple of days, and I want to make sure just everyone's kind of on the same page in terms of what you need to do for your simulation. Okay, so we'll do that today for maybe the first 30 minutes. I think the most important thing I want to do today is just to make sure that you know how to check your results, and so because part of the report is to report showing you figures of the pressure and those and the streamlines and things like that. And so I want to make sure that you know how to use peer review, what that's all about, and what to actually look for in your simulation results. Okay. But this week is the last week of lecture. So today, today I think I'll be talking for maybe 30, 40 minutes. The rest will be open office hours. And then on Thursday, of course, we'll be spending the entire time just on open office hours. Okay. All right. Any quick questions I can answer for people before we get started for today? Okay. All right. So first thing I want to do today is just to review kind of what we covered last time. So last time we saw some vascular as a group. We learned how to do a mesh, so that was kind of a big part of it, and we learned how to set up the simulation. Okay. One important thing, and actually, let me go ahead and bring up the PDF. Remember, you need to do 2 simulations for your final project, and so you want to do one steady state simulation and one pulsatile simulation. Okay. So let me go ahead and bring that up. Version. Okay. So these are the project specifications. So, last time we talked about, going computing your boundary conditions. Okay. One thing that you'll need to do is you need to run one steady state simulation. Basically, what that means is that your inflow condition is going to be steady. Okay. And one pulsatile simulation where your inflow condition is going to be changing with time. Okay. So the main way that you're going to set that up is that you're going to basically change your inlet boundary condition. Okay. And so if you go back to the simulations tab within Simvascular, so within the Simvascular kind of main graphical user interface here, and you go to your job here, okay, there's one part when you set up your simulation where you double click on your inlet face and you have to select the flow file. Okay. So there are 2 flow files. So actually, if you go to the Canvas site, actually, let me show that really quick. So if you go to our Canvas site here, you go to the Files tab on our Canvas site, and you go under SimVascular, okay? You'll see that there are two files here, right? So there's one cap_aorta.flow. This one here you're going to use for your steady state simulation. And then we have the generic pulsatile inflow. This is going to be for your pulsatile simulation. So you're going to need to download both. Okay? And the way to use that is that when you're going to run your steady state simulation, let me just go ahead and do that here. Okay. When you run your steady state simulation, you're basically going to set the flow file here to be cap_aorta.flow. Okay. And then when you're going to run your pulsatile simulation, you're going to change this flow file to general pulsatile inflow.flow. Okay, so that's the main thing you're going to do to change the conditions between your steady state simulation and your pulsatile one. The other thing that you have to do is you have to change the number of time steps. Okay. Okay. So for your steady state simulation, and in fact, I suggest you do it like this. And so, under the simulations tab here in SimVascular, you can actually make multiple jobs. So actually, let me go ahead and create a new job, and we'll call this one the steady simulation. Okay. So under the steady simulation here, we have our basic parameters. We have our inlet and outlet boundary conditions. Okay. So let's say that we're going to set this to be our usual cap_aorta.flow. Okay. And then for the outlet boundary conditions, we're going to split those resistances. Okay. So just like we did last time, we're going to right click on our outlets. We're going to split resistance. We're going to enter the resistance we're going to split. I'm just going to enter 1200 for now. Okay. Our wall properties are going to be rigid. Okay. So for your steady state simulation, we basically just need to run the simulation until it reaches steady state. Okay. And it usually doesn't take that many time steps to do that. So the number of time steps that you're going to set for your steady state simulation is going to be 100. Okay. That's all you probably need to reach steady state. Okay. Your time step size, just like before, is going to be 0.001. Okay. And the number of time steps between restarts, you're going to set it to be 10. Okay. All right. So that's for your steady state simulation. So let me go ahead and make the pulsatile simulation just so you can see it. Okay. So I'm going to make a new job right here. I'll call it a pulsatile simulation. Okay. So under pulsatile simulation, okay, most things are going to stay the same. In fact, let me go ahead and set the outlet resistance boundary conditions. These are going to be the same. So let me split this resistance. Let me set it to 1200. Remember, for your models, you're gonna split the total resistance is going to depend on your patient's blood pressure. Okay. For cap_aorta, we're going to set to prescribed velocity. All right, so here's where it differs. And so when you go to set the flow file for the inlet boundary condition for your pulsatile simulation, you want to make sure you use generic pulsatile inflow. Okay. So again, that file is available for you to download on Canvas. For me, I just know that it's in this folder right here. Okay. And there you go. Okay. And so that's how you set the pulsatile inflow. The other big difference that you're going to need to make for your pulsatile simulation is that the number of time steps you're going to need to set it to be 4,000. And so for the pulsatile simulation, we actually need to run this for 4 full heart cycles in order to reach, a good converged state. Our time step size, once again, is going to be 1 millisecond. And the number of time steps between restarts, we're going to set it to be 50. Okay. So make sure you note these differences. And so when you're running your steady state simulation versus your pulsatile simulation, you change these accordingly. Okay. So for steady state, the total number of time steps is 100. The time steps between restarts is 10. And for the pulsatile simulation, the total number of time steps is 4,000. The number of time steps between restarts is 50. Okay. And I need you guys need to run both of those simulations for your final project. All right, any questions on that so far?
110, 4,050.
Exactly, yeah. Mm-hmm. Okay. All right, so next thing I want to change from the last time is that I've been doing some testing on the cluster the last couple of days. Seems like the cluster is kind of on its last legs, and so a lot of the computers there I think are getting old. So they're not as powerful as they used to be. So the thing with these high performance computing clusters is that they generally age over time, and they lose performance. And so the one that we're using, it feels like it's kind of near the end of its life cycle. And so we need to be a little bit more gentle with it. So we need to not give it such a hard simulation to do. Okay. So that means basically we're going to use a little bit different settings here for everything else. Okay, so for the step construction, this one's going to stay the same. So for the step construction, we're going to set that equal to 5. Okay. The residual criteria, we're going to add, we're going to keep this the same as it is right now, actually. So I think before we set this to be 0.001, but for now, we're just going to set this to be 0.01. Okay. The minimum number of iterations, we're going to set this equal to 2. And by the way, these settings are going to apply to both your steady state simulation and your pulsatile simulation. Okay. And then for all of these tolerances here, so tolerance on the momentum equation, tolerance on the continuity, tolerance on the SVLS, okay, we're going to set all of these to 0.01. So previously we had these at 0.001. We're going to loosen that up a little bit and make that 0.01. All right, and then lastly, for the maximum number of iterations, so this is setting number 26. Previously, we set this to 10. 10 is a little bit overkill for this, and so we're going to set this equal to 3 instead. Okay. All right, so that all looks good. And so just like we did last time, we're going to create the data files for the simulation. So one big thing that a lot of people have been asking me, especially if you're on a Windows system, is that you may be running some errors. And so when you click on this, you may get an error that says the files failed in producing. So make sure you check the email that I sent yesterday on how to fix that. Okay. But if you implemented that fix, or if you're on a Mac computer, then you should have this. And then what that allows you to do is that produces your simulation files right here. Okay. Okay, so we're all good to go. Okay, so last time, we kind of ended around here, and I kind of showed you how to use the gateway, but I didn't actually show you how to actually download the results from the gateway itself. Okay. So a few of you have already had a chance to run your gateway simulations, and if you haven't had a chance to make your account on the gateway, I would definitely do that. And so if you haven't made your account yet, go to gateway.synvascular.org. Go ahead and log in with your Cal State Fullerton ID. So there will be a time where there will be a part where it's asked if you want to log in with an institution's credentials. You can choose Cal State Fullerton for that. Okay. And the way you run the simulation, remember that you click on this, you upload all your files here. Okay. You're going to set the number of cores, and so the number of cores that you can, I think the max for you guys, because you guys are kind of student accounts, the maximum number of cores you can use is 72. But again, base that off the number of elements in your mesh, and so make sure you use an appropriate amount. And your wall time limit, I would just go ahead and max this out and set it to 1200. Okay, but we did all that last time. So let's talk about what happens when you actually complete a simulation. Okay, so I finished the simulation earlier today. And when you finish a simulation, you'll see that there is what's called a tar file for you to download. Okay. So your tar file may be called something different. It depends on how many processors you use for your simulation. So for this particular simulation, I used 24. Okay, and so that's why it's called proc24.tar.gz. So go ahead and download this. Okay. Where you download it doesn't really matter, but generally what I recommend is that you download it to the folder where you created your project. Okay. So it looks like I already have it here. Okay. And then you're going to unzip it. And so these files, even if you've never seen a tar.gz file before, it's basically just a zip file. It's Linux's version of a zip folder. And so to unzip it, you may have to download a tool like WinZip, something like that. Or I think 7Z, I think probably works as well. Okay. Okay. But then after you unzip that folder, you'll have a folder on your in your computer called nproxcase. So actually, let me show you one that I did earlier just so that you can see. Okay, so after you unzip the folder, you can see here that this simulation I ran on 8 processors. You can see I have a folder called 8procs case. Okay, we now need to feed this this folder to Simvascor in order for it to convert our results. Okay, so if you come back to Simvascor here, if you'll notice in the simulation kind of workflow here, there's one tab that we didn't get to do yet, which is convert results. Okay, so let's go ahead and click on the tab, convert results. And you're going to be greeted with this menu right here. So the way this menu works is that, it's going to ask you to navigate to your results directory. And the little tooltip here says that this is the directory containing all the restart files. Okay. So if you click on these 3 arrows right here, it's going to take you to a file explorer. So let's go ahead and navigate. And the folder that you want to highlight in this case is going to be the nprocs case folder. So for now, I'm going to set this to 8procs case. And so I'm going to select this folder. Okay. So you can see here that we've selected the 8procs case folder. The starting time step is going to be 0 most of the time. Okay. And what you're going to put for the stop here is going to be the maximum number of time steps. So in this case, it's going to be 100. Okay. And then for this increment here, you're going to input this setting right here where you indicated the number of time steps between restarts, which is 10. Okay. All right. Okay. And then everything else you're going to keep it selected. Okay? And then you're going to click on convert. Okay? And so after you click on convert, it's going to ask you where you want to save the results. And so you can go ahead and save that into the appropriate folder. Usually for me, I just like to put this in the same folder that I made for the simulation. Okay? But it doesn't really matter. As long as you know where the folder is, then that's fine. Okay? It's going to take a little bit of time, and so give it some time. It's going to look like your computer's frozen, but trust me, it's okay. So while that's going, let's go ahead and download another program that we're going to use to view the results called ParaView. Okay. Okay. So I have ParaView installed on my computer already, but let me just show you where to download it. So I would just open up a Google folder, a Google tab here, and say download ParaView. Okay. ParaView is spelled P-A-R-A-V-I-E-W. You're going to click on this, and then you're just going to take you to a website here where you can download ParaView itself. Okay. Generally, I recommend one of the MSI versions just because that'll install it on your computer. And then it'll basically install as if it were just another app or another program on your computer. Okay. Okay, let's come back here. Okay, looks like everything's been converted. So I'll let you guys kind of download ParaView in the meantime, but let me show you kind of what it looks like. So ParaView is a software that's used a lot in the CFD community for viewing results. So are you guys using ParaView in 536? Yes, it's pretty common. So if you're in 536, you probably already have it on your computer. But this is basically how it is. And so you can think of it as almost like a 3D viewing type of software where, it's often used to view, 3D models, but we can also use it to view CFD results as well. Okay. So the way it works is that, when you first open up ParaView, it's just, you're going to open up to a blank screen right here. So usually what I like to do is that I usually like to go to the place where all of my results are. Okay. And so if everything converted okay in Simvascor, you'll see that there's going to be a folder called converted results. Okay. And you're going to see all these files here, and these files are either VTU or VTP files. Okay. Okay. So what I like to do, actually, let me show you this actually. So let me show you something cool. So let's go ahead and open up those files there. So let's go ahead and navigate. Desktop, demo project, SV project, simulations, steady converted results. Okay. Okay, let's load the VTU results. Okay. So the difference between VTP and VTU results, VTP only shows you kind of the outer surface, but VTU actually gives you the results all throughout, which is going to be actually really important. So I'm going to go ahead and click on this group right here. Okay. And so clicking on that group for all results _00 star, you're going to see that it's in bold. And so to officially load the results, you need to go to the left right here and click apply. And you can see here, this is our model. Okay, so right now it doesn't look like anything's happening, right? And that's because the model, this is at time step 0, where we've just initialized it. Okay. When you have time-dependent data, you can actually load your data in as a stack, and that's kind of what we did here. Okay? And so if you look at this part of the ParaView interface here, this is kind of the time bar here. Okay? So let me set this to the max. Okay, so you can see here we have a max of 10 files. So actually, let me go ahead and set this to 10. Okay. And you can see here that our pressure changed, right? And so you can see that the entire model is red, which may indicate that the pressure is very high. But if you look at the color bar for the pressure here, you can see it's between 0 and, well, 0, essentially right here, right? Because it's 1.2 times 10 to the minus 38, which is essentially 0. So what we need to do here is we need to rescale this data. And so to rescale the data, you need to click on this button right here. Okay? So if you click on this ruler here with the 2 arrows on it, you can see here that it rescales the image to the data range. Okay? Okay? So clicking that, we can see here that we get a much more realistic picture of the pressure. Okay? So you can see here that we have high pressures at the inlet and relatively low pressures at the outlet. So this is kind of generally what I expect to see in these kinds of simulations. Okay. Okay. And to view different results here, so what we're viewing now is pressure, but if you go to this section of ParaView right here, you can actually view different results. Okay, so instead of pressure, let's go ahead and view the velocity. Okay. So what we're viewing right here is the fluid velocity. Okay. You can see that for the majority of this model here, that the fluid velocity is 0. That's because everything on this outer wall here has 0 velocity. Because remember, we assume that we have no slip boundary conditions on our walls. Okay, and if we have rigid walls, that means the velocity is there is 0. But if you tilt the model, look at the inlet and your outlets, you can actually see that there's some fluid velocity in these parts. It almost looks like a piece of candy or a piece of Tootsie or something like that. Okay, so that's the velocity. The other thing that you can view here is the wall shear stress, which I expect a lot of you to have in your final reports. Okay. So remember, the wall shear stress represents the viscous shear that the fluid is imparting on the vessel wall. Okay. And so you can see here that there are areas of higher shear in red and lower shear in blue. Okay. Okay. So these are all really important. And so when you go to write your report, you can see here that I'm having you view basically the pressure plot, the wall shear stress plot, and the velocity streamlines. Okay, and so you need to basically display all these figures in your final report. But more importantly, I want you to comment on them. Okay, because what you'll see, especially for all of you that have some kind of disease in your model, whether you have a coarctation or maybe you are a cerebral model, so you have a risk of aneurysms. There are certain areas that are going to light up in your simulation here that are interesting from a fluid mechanics point of view. Okay? For instance, so a lot of you have models that have a narrowing in the blood vessel, right? So whether that be a coarctation, so a coarctation is in the aorta looks something like this. Okay, so the vessel gets really tiny. Or some of you have an aneurysm. So some of you have aneurysms that kind of blow up like this, right? And so I want you guys to look at the pressures. I want you guys to look at the wall shear stresses within these regions and tell me how that's correlated with disease, okay? And so what you should see is that, maybe when the vessel narrows, the flow has to speed up to get through that narrowing. And so you'll probably see an elevated wall shear stress. You may see a pressure drop across the narrowing, okay? For an aneurysm, you might see the opposite. You might see a low wall shear stress on the outside, and maybe the pressure doesn't go down as much, or maybe the pressure does go down. Okay. So this final report here it's more than just running the simulation. I want you guys to correlate your simulation results with the biology, with the biomechanics that's happening in your models. Okay. So I would definitely reference a lot of the lectures that we've had previously in this class. You can look up just articles about, coarctation and what that means, the wall shear stress, the pressures, and what that means. And I want you to correlate kind of what you're seeing in the simulation to that disease. Okay, so that's really, that's an important part. So I don't want to just, I don't want to just read your reports and just have a bunch of figures of these. I want you guys to actually connect the simulation results to the biology, to the biomechanics. Okay? And in fact, if you read kind of the project specifications here, I have a lot of discussion questions that kind of, walk you through that process. So make sure that you not only show me the figures, but you also answer these questions as well. All right, any questions on that? Okay. All right. Other thing that I want to show you is that one of the other results that I want you to show is the velocity streamlines. Okay, so let me show you how to do that, because it's a special filter that's actually in Paraview right here. Okay. So to view the velocity streamlines, you need to use a special, we call a filter here, and you're going to use one. If you can kind of see where my mouse is, actually, let me circle it with my pen here. You're going to use one that's called Stream Tracer, which is this one right here. Okay, so after clicking on the Stream Tracer filter, you can see that a big white arrow appears, but we actually want to do this with a point instead of a line. Okay, so to do this with the point, you can see here that's one setting right here called interpolator with point locator. Okay. Actually, wait, that's not the right setting. Let me see. Sorry about that. So the setting that you want to change here is called the seed type. And so instead of a high resolution line source, we're going to change this to a point source instead. Okay. And so changing it to a point source, you can see here that we have this little sphere that we can kind of move around. And so you want to move this sphere up to the inlet of your model. Okay. If you have multiple inlets, you can just choose one of them. Okay. But what you'll notice is that it's actually kind of hard to move the sphere, with your mouse to the inlet. Actually did a pretty decent job there. Okay. And so one shortcut that you can do to snap the sphere to your inlet is to mouse over your inlet and hit P on the keyboard. Okay. And so hitting P on the keyboard will snap the sphere to your whatever face that you clicked on. Okay. Next thing you want to do is you want to make the sphere a little bit smaller. So to make the sphere smaller, you're going to mouse over the sphere and then right click. And then as you click and drag with right click, you can make the sphere a little bit smaller. So you want to make it about the same size as your inlet. It doesn't have to be perfect, but you don't want it to be way too big. Okay. So once you do that, I'm going to go ahead and hit apply. And then after I hit apply here, you can see that, we have these lines that go through, and these lines kind of show you the path that the velocity is taking. Okay? And you can even color this by velocity as well. So to color it by velocity, you're going to have to go up to this menu right here and change the coloring to velocity. And then with that, you should be able to see the path that the fluid actually goes through in your model. So for this one, it's not that interesting just because we have just two outlets. And so the flow really has no choice but just come from here and go out to the outlets. But for some of you that have kind of, the cerebral vasculature in particular, those of you who have aneurysms, the pulmonary ones, the congenital heart disease, I think you'll see that your streamlines are actually very interesting. Okay. And you can play around with the settings with these too. And so if you want to add more, more streamlines, you can do that. So we come back to the stream tracer here. You can specify the number of points. Okay. So right now we have 100 streamlines there, but you can actually make this even more crazy. So you can make this like up to 1,000. Okay. So if we change this to 1,000 and we hit apply, takes a little bit longer to think about that. Okay. You can see here that we have a much denser picture, and you can even make it less. So actually, let me make this like 30. Right, so you can kind of play around with it to see the density of the streamlines itself. Okay. And if you have a situation, sometimes this can happen where the streamlines don't make it all the way to your outlets. You can actually change the length of the streamline as well. And so you can see here there's a setting for the maximum streamline length. So right now it's set at the default of 34. And so if we increase this, so we say we increase this to 100, okay, the streamlines might go a little bit further in that case. Okay. All right. Any questions on any of this? Okay. All right, one last thing I want to show you guys, just and unfortunately I don't have the data for it right now, just because I'm actually running the pulse health simulation on the cluster right now. The cluster is so much slower now. How to view the pulsatile data. Okay. So remember earlier today, I mentioned that this kind of bar at the top right here, this bar represents the time that you're viewing for your results. Okay? And so if you move this to different numbers here, it's actually going to show you the results at different time points. Okay. So you can see here that I'm clicking on it, but nothing's actually changing here on this image right here. That's because this result right here is for a steady simulation. So it makes sense that all the results show the same thing because it's steady state. But for your pulsatile simulation, the results here are going to change at different time steps because the amount of flow that you're putting in is changing with every time step. Okay? And so for your pulsatile simulation, if you want to move to certain points right here, you can use this bar. And what may happen is that you may have to rescale. Okay? Because you may move to a different time step right here, and your entire model may show up red. That it could be just that the entire pressure is much higher. So you may have to hit this rescale button right here, to rescale the colors appropriately. Okay. All right, and so that's about it. And so that's just kind of just kind of wrapping up everything else that you need to know about downloading your results, how to set up a pulsatile simulation, converting the results, and viewing them in parallel. Okay. All right, and so for the rest of class today, I will be going around the class, and just if you have questions on your project, questions on your mesh, setting up the simulation, I'll go ahead and answer that. If you're on Zoom, just go ahead and leave a just leave a message in the chat, and I'll come around to it eventually. Okay. So if you have questions, just raise your hand, and I'll come around. I'll come around to you.
Yeah. Yeah. So we'll I would put it on the one that gets. So the first time step probably got to see so go ahead. Yeah. Yes. Yeah. That was for no, I would do that if you do the 0.001. I would suggest it's just yeah. When you screenshot, make sure you have this one. Okay. Okay. What's that? I didn't notice that yeah, it's the same thing. Yeah, it's the same thing. Yeah. So if you open up, so that doc profile is actually a text file. So as long as it's like, well, you can't open it from here. But the if you open up from the file explorer, just open up in like Notepad. Just go to simulation. Actually, so actually where I got that one is that every time you make a simulation, it makes a profile as a second file. It's a Notepad. So you can see here it's 0 minus 1. So, I mean, you can double check it just to make sure. But the one that I posted is, or the steady state one should be this. But the pulsatile one that I posted on Canvas is going to be the data here.
question.
Yeah.
When I walked in, I could hear those. Use the resistance.
Yeah. Yeah, so go to your inlet and outlet boundary conditions. Yeah, so for you, you have a lot more. You also have more. So that's gonna be a challenge. But you need to basically determine which ones are out. For the outlet ones, you have to change the type. So if you double click on that platform, click on the down arrow, you can see that we're basically only going to be worried about the first two. So the first one, it's kind of cut off. The first one called prescribed velocity. So that one you're going to put for your units.
No, I need to.
Yeah, and then for your outlet, you're going to change all of them to the second option, which is resistance.
So it'll just be like one inlet.
Well, for you, you're going to have two inlets. So you actually do maximize your velocity. So your two inlets actually, so this is one inlet right here, and this is the other. So you're gonna have flow actually coming from both sides. Everything else here, everything else that's pumping right here is gonna be.
If you click these.
Yep.
Corresponding.
Yeah, so that's your other. Everything else should be resistance. Right, so go ahead and change all of your outlets to resistance for it doesn't know. Okay, so then hold control on your keyboard and highlight all the resistance outlets. And then split resistance. Okay, so here you're gonna enter the total resistance. So the total resistance can depend on the patient. And so basically what the pressure was based. I think that's pretty relevant for you too, because you have a really young patient. So I would make sure that kind of double check. If your PEM doesn't show what the pressure is, then this baby's probably like 1 or 6 month old. Yeah, usually 6 to 12 months is usually. So you can look up the blood pressure. Use that to compute the resistance. So the formula for that is the Hodgkin's test.
Okay, that's not one.
No, it's this one. So this is overall total resistance. Blood pressure, and then for the flow rate, we're just going to use 100.
And the Murray's law coefficient is
It is technically, but anything between 2 and 3 is probably okay. Probably for the pulmonaries, I'd probably say something like 2.4, 2.3, 2.4. I think is probably good. It doesn't make that big a difference if you're kind of 2.4, 2.5 doesn't make a big difference. 2 or 3 make a big difference, but I think yeah, 2.4, 2.5, 2.3, that's all pretty.
and then just calculate the resistance.
Exactly, and then that'll give the volume resistance on.
Thank you.
Yeah,
I would just have I'm just having one, so there's some, not looking at this one.
exactly, yeah, and then everything else.
Part is technically like right here.
Exactly, yeah. All the order models have the same.
And then everything else is just.
Exactly. For rabbits, this is rabbit.
Yeah.
Does it have the blood pressure in the?
It was very precise.
If not, you can look up what's the blood pressure in rabbit. It actually might be pretty consistent. I think blood pressure is actually pretty consistent across species, interestingly.
That was it.
Okay.
That's all.
I think blood pressure is pretty consistent. I would just maybe do a quick Google search, like what's the average blood pressure? I'm guessing someone probably can answer that at some point. Oh, yeah, it's actually,
Like, so what do you think?
yeah, it's actually basically
A
the
little
same.
higher.
Maybe a tiny bit. Yeah, blood pressure surprisingly is very consistent in most species.
So 70 to.
I would go maybe somewhere in the middle,
Like,
like usually 90.
100 or so.
100 is fine. Yeah,
110.
usually on the lower.
Okay, so. What would you put for that?
So you need to use that to compute the resistance. Basically, you're going to take that pressure, which is typically in mmHg, you're going to multiply by 1,333 and then divide by 100. That's going to be your total resistance.
Okay, so, sorry, by 1,033.
Yeah.
Divided by 100.
Yeah, that's the formula for that's in the
And
project.
then I just split it between all those.
Exactly. So actually the program was split it for you. So if you highlight, basically just do the same thing as Daniel, where you highlight everything, and you right click.
Some of the resistances.
Yeah.
Something with pressure. Use strategy of the program.
Yeah, actually, so your patient actually does have pressures. That's good. So I would use this column right here. So IVC stands for inferior ventilator, which is your main. Okay. I would use this. That's good.
Okay.
That should be 1,300. The 90 is the blood pressure.
Yeah,
The
that's
1,000. Yeah,
That's a conversion.
exactly. And a 100 the first year getting put in. It's much well. Most people can do.
Just a bit more.
And then your Murray's law, maybe like 2.2, a little lower, so 2.2. Yep, so all your outlet coefficients.
And then as you said, just be honest.
No, so that one you need to do the flow. So double click on.
Actually, I don't think I'm on it.
Okay, yeah, it's on.
It's on my case.
Yeah, so you have to go to the files folder. I think it's under Symbascular. Yeah, it's under Symbascular, and then there's a couple of there's one
There's a
steady.
pulsatile.
Yeah.
And then that's what you're doing.
Exactly.
And that's how you open.
Yeah. No, I can just do like.
Yeah, wall time just to make sure that. I think with these new settings, I think probably will take 6-7 hours. But so it shouldn't, so 1,200 minutes, that's 20 hours. A couple guys already ran 20 hours to do just the steady.
On their computer, right?
No, on the bus.
On the bus.
Yeah.
I actually did ran one in like. I did run one.
Yeah. Yeah, that's 200,000. Yeah, that's pretty. That's close. Yeah. 1.6, we definitely want to. Yeah. I see. Yeah, you mentioned always the hardest part. Yeah, I see that.
I just, you take your average,
This is the model.
and you multiply by those, this is divided by your things for.
Okay.
So take like whatever the average.
Oh, millimeters.
Yeah.
It's that one, that's like, dude, that's like, you're about to.
I'm checking the areas, so you actually highlight the services. The service. The basic things is way, one rough way to measure this, that I will see the surfaces of the lowest, area, and then basic side, they measure the area.
Oh, I'm thinking. Oh, what time you see?
Looks like there's a small.
It's
This is like day order pressure, so that those.
Yeah, that makes sense, but this is like.
It's not that bad.
Yeah.
I think what maybe happens. This maybe. You see how the models like. So what can happen with, so what happens in the mesh that it basically takes your genome, you've got your whole places. But the Legos kind of have to be during the shape. So what?
Where's the
On this twice, but we did the.
the velocity path?
It's kind of. It's really hard to triangles rolling off the bottom.
No, yeah, that's what I'm. You have to download the,
Positive.
like the folders, one for Denny and one.
Sometimes if the engine not too bad. This one might be a little bit tough to actually.
It's in the.
75.
It should be.
It's on stage, it's on
So I think what I would try, so I think the main focus is has to be that it's like right here. So you can see how it's kind of, it's not a positive slope, because it starts out kind of wide. I would maybe. Like what tends to happen, and this is always a challenge when we. Also, there's always one side of the region, so there's these three ends right there. So when that happens, I would actually err on the side, let's delete this one. Let's let the guy one, this segmentation, that would probably smooth that out, because then. Yes.
So capture with a
see.
Did you put in the same circle?
Yeah, you can see how it's this, yeah, this one's happening because these two segmentations here are relatively straight, but then this one's kind of. I think that's fine, because the vessel, because usually you want to add segmentation. That's what you it's within the direction. But it looks like the vessel not changed. So I would maybe. Yeah, I think those should probably. I think this one would make quicker to make. That if that's the one. Maybe just do. Any section.
I just need access.
Okay, yeah, when I get back here.
How do you?
So for the rad one, we're not able to.
Actually, we just looked it up. So blood pressure actually surprisingly very consistent across the animal species. So it's very close to human species. So you can use just like. So I think you're using 100. 90, yeah, 90 is 3D. Yeah.
You haven't really.
Yeah, because that section, that's actually on the penis. So veins.
Oh, it's on the other side. It's on like the whole there.
Yeah.
Coming back.
Exactly. Yeah, so the order actually, that's the max blood pressure, that's the minimum. So veins are gonna be much.
Yeah, it was like.
Also,
It was like 8 and
Yeah, yeah.
9.
That makes sense. If it's on the bus, it's really on the side. Yeah.
Yeah, I mean, so base here.
I didn't know it's like, I get out there, I mean,
Okay, that's like, you told me to use my mind. Oh, gosh, I want that. Yeah, I think this is good. Yeah. This is the mesh takes a while. And so when you close it out.
When he just emailed them. Yeah, the song.
Yeah, I think we should be good. I would go ahead and start. So yeah, is it the same for? Yeah.
Yeah, that's. Then once you know.
Yes. Yeah.
Looks like it's. Yeah, go ahead and try it now.
Thank you.
Just on to. Yeah,
But the way you stay on, it's still like.
Yeah, so the steady one.
There's a doc profile, it was for general profile.
Just reset your.
No, it's on Canvas. Go to Canvas.
When.
Oh, right.
Ask him if, it's just a text. Or is that easy to check? Yeah.
Make it small, you like it.
Something.
It doesn't have to be exact.
I think he might have.
You know what?
Mr. Academic Dishonesty.
I know.
No, well, I thought he was asking about the conflict. It would no, it was.
Yeah, because you have three of those. Oh, yeah. Because you have three inches. And the other thing I would do, because it looks like it does the screen. Yes.
I'm not sure if like I'm ready.
Number one.
No, I'm actually working with, because all you have to do prior to it is model.
Yeah, model, like in the water.
And then what's
Oh,
next?
wow.
You can play with it. Yeah. So you just throw it in the, but you have to put your parameters. And that's just based off of your reading. Yes. So it's part of the combination of
So here's the rabbit.
mine's a given. Mine's the one where I use. Like conditions. Yeah, I think it's one.
Like it's.
And I use a lot.
I got
I do such a yes, so like that, and then he might just say.
And the only thing I didn't see was it's out. So I had a one study.
So yeah, usually it's where, it's usually because there's one place.
I was thinking.
There's probably a part where. The caps are okay. Maybe like somewhere, maybe this really did do as good a job. Maybe you want to try smoothing it a few more. I think the elements are just. So basically what happens when, so the way it works is that the mesh generates all the elements. But it doesn't do a good job of making sure you don't have right. So what they have to get a vessel your vessel that kind of like this, like consider the intersections. And it causes that. So I would check through this area. What was the thinking is that?
Like between both sides.
It should be nice to do this.
The only thing you change is that velocity.
It's a little bit sharper than see. Maybe because of these here, these two things, maybe with most between the two. Yeah. So I personally think if it's still having issues, you want to try to.
Well, I should have his
last one. It's the one of the years.
Yeah, I'll just add it.
Just so you really know what's watching there. Not too much smaller, but just small.
I remember he was like going on to slides too.
And try relocking.
All right, sorry, Zoom people, who's still here? Caleb, the tar file is the zip file. It's just a kind of a specialized version of a zip file. So you would download the tar file and then you would open it up using either 7Z or WinZip, and then it'll unzip it into a whole folder. All right, Sumit, so for the increment, you're going to put the number of time steps between restarts. Wait, sorry, was someone talking? I kind of heard. Okay. Oh, okay. I see. Hang on, let me approve Brady's account. Okay, Brady, you should be good to go.
Cool. Awesome. Yeah. Okay. So I needed a little closer to the 1 million. Actually, with the way the cluster is actually being on the lower end of the elements. Okay. Because I'm running a simulation with 2 million right now. It's taking all afternoon. So 1 million actually would probably should have. Should be okay. Just maybe run it overnight. Just to yeah.
I'm planning to hopefully send it and then I can work on it.
Yeah.
I didn't have any.
Exactly. Yeah. So basically,
I'll probably finish this up.
Perfect. Yeah. Because so once it's on the cluster, it's running off of your computer, so you can turn off your computer and it'll. So I think actually at the bottom when you make a job, there's a ticker. I should have shown you.
It's you sent one and it started running it already.
Oh, perfect.
And
Okay.
he was able to see that it was like.
Oh,
that it
good.
was
Good.
already progressed.
Yeah, the cluster, I mean, because it's used by so many different groups. So sometimes it's super busy. I think this afternoon.
Does it go into a queue?
It does. Yeah, there's a queue.
If that's the mayor will. See, these are senior advisors for Rocket.
Yeah.
So we have a meeting. And I think kind of manages on, but. Because our final for is so like ours.
Yeah.
Yeah.
That's cool.
It's so, I mean, it is steady state, so
Yeah.
it's not bad, but, it's just turbulent.
It's
turbulent. Our meshes are not. Like, we're running it like in parallel.
Gotcha. I see.
Yeah,
Yeah, it's,
He was
If he's
thinking about trying, he said he was gonna talk to you about this, kind of.
Yeah.
Clusters so we could do more intense, like finer matches.
yeah, that takes a while to set up. So probably do that. Because this, I mean, this took me years to kind of set up, so.
No, I was telling him like, it's a very simple portal, so you don't have to use it like. terminal windows.
Yeah, it's nice.
Because we're doing, he's gonna show us how to do a back file.
Okay.
So we can run like 6, 7 steps of overflow, like in some.
I see.
Because we have to run like. Refine now.
Oh, and
Surface feature.
your guys' computers are gonna be crying over the next 2 weeks.
Well, we're splitting it up, two simulations per 3 computers.
Okay. Yeah. Okay, so your total file simulation is total file. Yeah. I would change this to 5. And then just to make it a little after the no changes.
Are you doing
Yeah, yeah, everything down here.
except for the 4,000?
Exactly, so for all of these ones, these are kind of the same thing as the different period. We want to make sure they all match. So I put everyone in
I don't have any of those.
Yeah, I'm gonna change that. And this one, before I set this to 10, honestly, if this were like a research thing, I don't think. But just for fun, I just change it.
I don't have a place to.
At least, one is too small. Yeah.
Hi, Professor.
Okay, I'll be back.
You don't have a. No, I know, but there's a.
Yeah, that's it. Yeah, and then this experience is how we get to. Exactly. Yep. You go back.
I think I have this actually.
Yeah.
So,
I think for one day you can try. Or your submission. I would maybe make this higher. Just so that it crash. Does it crash? Well, we did this crash.
It crashes.
Oh, in that case, the mesh will probably just take. So just let it run. That actually is actually very intensive. It's very intensive. So it's gonna look like it's awesome. If it locks up, it's better than like 20 minutes then. So. But it's only been like 1, 2, 3 minutes.
Should I run it again with a system or just
I would try maybe 0.15.
zero?
Maybe Thursday, okay, this one Tuesday, like maybe. Oh, yeah. What this is gonna do is that basically you kind of shrug it there. Sometimes this can get, so someone back there, they had some, seems like this kind of. Okay, I'll go ahead. I'll go back. All right, sorry about that. What's up?
Hi, Professor.
Hey.
So yeah, so in convert results, the stop should be basically the number of step size, right?
Yes, the stop should be the number, total number of steps. Yeah.
Okay, I'll go right.
And then the increment is the number of time step between restarts.
Okay. Sure.
The only thing that's in the
Still-
rules
still
are
maybe-
reservations.
So I used to do this all the time.
I don't know.
Let's make kind of individual models. of each lesson. So usually when it's
Maximum
something like
relationship
this,
with solver,
one
but that
piece
is
per
per
lesson,
student.
maybe it's not. Probably. Now let's add, let's progressively add.
How you change it is, so.
Let's progressively add more of that. I'm not gonna do this. That's good. Go to one more motion task. This is expanding. Okay, but yeah, I would add to that. Sometimes we can actually fix it. So for some reason, doing it one by one, I have that happen. Meshing is like also spectrum, you gotta be exact. So sometimes you might just pick one, or sometimes you might get one, you might produce a mesh. I would think you do that. Solve some of this, or at least tell you. Oh, okay. Thank you very much. I'll come back. Yeah. That should just be on. Yeah, just max it out. It's 72 max. Yeah. Okay. Right, yeah.
So then I
I've been measuring.
No, I think it was almost. It's not bad. You say when you're at it, you're at 2. With every model is slightly different size, so it's hard for me to recommend. But at least now you have a reference. One side, 0.15. You probably need to go off. Sometimes with the really coarse meshes, it could be a thing. Sometimes the triangle just.
So can you see?
So maybe we just.
And I think you. See, like, I think the geometry.
I think 1.5, sometimes they're there.
You start.
So this is actually pretty, if you want to run it.
Yeah.
Yeah.
Then you take this research file. Like there, that.
Here probably we can do faster. So let's take this down.
Look up the little selection, this kind of tells you about BCT.
So the,
once
never measured so if you just start with that, then.
Oh, I do.
This was gonna take. I would read this first. But this next part, but as long as it's still agreed, zero it's still.
Yeah, so that's the small one.
Yeah.
The one I don't think that, I don't smooth.
This one, it might just be a little close. Yeah. Yeah, it looks like it's just a little, maybe make that one. Okay, then let's try smoothing these two.
Is there any idea?
Let's do it to general. For now, we just want to select, okay, so all before. With just these two selected, we can do a little bit more aggressive, so we can. The next aggressive, so we match the Boston. We don't want to do just our two inches, like every time we hit enough, we would actually, kind of shrink it. That's just how this movie. The extremes will actually, one of my good friends actually. It makes sales that's only going to be very good. But the velocity lag is. One of those. 2 times. Especially when. It can be shrank too. Yeah.
What's your name?
Okay, let me talk to them. Let's see.
Since I already did the, what you want.
Yeah. Yeah. You do too. Yeah, steady state. So the steady state will cover. Right now, the steady state one, was just. The post one's actually going to go up.
Has to do with some state, the simulation.
For both of them, it's steady state, or
Yeah, Richard Walsh.
One of the, how do I say all of this?
Oh. You can save the state, so you can save. I would save it the same.
We're both getting the same issue, so we're not having any geometric patterns, so we're just getting them to start, this one there.
Oh, what happens, so when you go to semester, when you create the simulation, what happens with it?
So that's, I think it's fine, it's just, it's putting me through like, just, so it's like a weird, important piece, so I just have to figure it. And then when I put it down to that. So like, closes, and then it's like, data file, maybe that is.
Every time I teach new issues come up.
No, you consider.
Maybe I think it was beautiful. Again, same effect here. Even if I don't, it's still within the file. It gives you.
Yes.
We just, we reported the. So it's really like, companies, this five, we just don't,
You don't have to. That's what all the evidence. Can you show me that?
The volume, it's just.
Oh. Oh, okay. Oh, you have to actually, so this is an application that you have to install.
Oh,
Okay, double click this. Let me put it
okay, now I, and
there. It is.
we went through all this one bag,
Yes.
and that's what we have to do.
Yeah.
Now we just.
As we saw, we only. No, we're really close. You don't need it now.
Now that.
Let me do it. Okay. So you just download. If you want to try running on your.
Yeah.
Okay.
I have almost 3 minutes.
Okay, that's a little bit too much. So maybe we'll do 0.04. Just kind of play around with that a little bit. Looks like it on. Yeah, so for the meat flow, we're just gonna. Okay, so for this whole top one, it's scales as. Yeah.
Yeah, it's just so.
I wrote it. I can't just say.
Oh.
That's fine. Actually, you probably want to be on the roll. Cluster is.
Oh, and then also.
I don't have.
For the position of.
If you don't have one, not all of them have to. Right? You can just use it's around 9. I'll just leave.
Would you ask how many?
Okay.
Divided by 20,000?
Yeah.
So how much?
Yeah. I'll start also.
I think I'm good. I'm at 2.2 million. I was gonna round that.
Wall time, I would go ahead and, so it's too much, we're gonna take more. 1200 is 20 hours. I'll go ahead and do 20,
Just, I mean.
it might take a bit longer to get around to 3, but right now we're still a bit small, I would say. And you can see how long your simulation takes. You can,
So we'll hold it out,
Yeah.
and there's no like.
there's no option.
But you don't, that's the only spaces in the sim mask, like. You don't have to do anything.
No.
You know how there was like that's pretty solid.
Yeah. It just goes long. Just leave it.
So just saying the
Very much. Yep. All right, guys, so we're out of time. So Thursday, we'll do this again on Thursday. We'll just have kind of open office hours. I forgot to announce, but I am gonna have office hours next week too. They're all gonna be all virtual. They'll just be at the usual time zone. Okay. All right, thank you, everybody.
One, for two similar, one study, and one.
Yeah.
So studies that took everything.
Yeah.
I don't want it.
Well, the postcard, I mean, the postcard one, we're just gonna change the profile. You're gonna change the number. Just kind of go back and watch it. Yeah.
In the video, you show how to put it into the.
Yeah, I just kind of walk through.
I just matched my sheet.
I have 20,000. It says like 100 doors.
Just max it out at 72. Yeah. It'll just take a bit longer, but that's okay. Executing basically means it's submitted the job, but you'll, there's a checkbox at the bottom to send an email updates. Did you check that one?
Yeah, I did.
Okay, it'll send you an email when it actually starts. Yeah, the cluster is pretty busy today, so it may not start till later this evening. Yeah, it's out of your hands now. Now it's running on the cluster. Yep.
So when, like, when it's like done, will these be filled in?
Exactly. Yeah.
So we can't tell how far it is, it's just.
You can. So once it starts, there's one field for the out.
Oh, that's executing?
So that actually covers that. So you go down. Yeah. Then. Okay. It may still, it may not.
Actually, I don't know what.
Steady state to be run, not just on it.
I mean, maybe because I'm an editor. Once it actually starts, then this thing is not vegetables. And once it starts, there will be a bunch of text, but then in the first column there, you'll actually be the time step that it's simulation. And so for your steady state, it's going to be the time. So you can basically gauge how close it is.
Okay.
Yeah.
Thank you.
Yeah. Yeah, no problem. You guys.
I'm concerned that my dad's not related, like. I'll just work.
Yeah. It's when I even have to figure out computers. Oh, there it is. Yeah. Yeah. I'm gonna post it that way. Yeah.